Okay, so fine. So we are recording today's session, started recording today's session as well. I just request you just to, in case I forgot to start the recording, please remind me to start the recording. Otherwise, we will lose this session. So strong motion instruments. So one is of course what you are all familiar with is the acceleropgraph. And second one is what we call as seismoscopes. Originally it was designated as seismoscopes by USGS, United States Geological Survey, and original design was by USGS, and then we designed our own version of seismoscope that was called structural response recorders, SRR, right? And this was done by DEQ IITR. So as we told, we were discussing that what we really look for is the maximum response of structural system. And of course this depends on the natural period of the structure. Natural period and damping, the energy loss mechanism. So what is done in structural response recorder is we have SRR is essentially 3 oscillators. Three pendula, penduli or penduli, what is the plural? I guess pendula should be the plural, but anyway, 3 penduli of natural period in the range of 0.40, 0.75 and 1.25 second. So these are the 3 natural periods, and for damping ratio 5% and 10%. So total there are 3 oscillators of damping 5% and another 3 oscillators of the same natural period of 10%, and these are arranged in a box so these are the simple pendulum, 3 pendulum of 3 natural periods, 0.4 second, 0.75 second and 1.25 second of 5% damping, and another set of the same penduli, 3 natural period of 10% damping, and it is essentially a pendulum with a smoked watch glass. So on top of it, this is a top of this pendulum is kept a smoked watch glass, and on top of it there is a needle on which will rests on this smoked watch glass. So in case of earthquake, this entire system, entire box base plate, I mean all these are mounted on a base plate, and in case of strong earthquake, these penduli will vibrate in response to the earthquake, and the needle resting on top of this watch glass would generate a scratch on this, some kind of scratch like this. So at the end of the earthquake, we would just go and measure this scratch, maximum scratch length divided by 2, and that gives us the spectral displacement, maximum displacement response, relative displacement response of the oscillator of whatever natural period. So if I get this for all these 6 watch glass plates, then if you look at this pendulum, what you saw in last week's lecture, the response spectrum that we plot for maximum response of different oscillators. So you get the 3 points on this response spectrum directly from this reading. So no need of any trace. Of course, the time axis is lost in this, and we don't get the time record, but we get the engineering information. What is the response, maximum response of the oscillators of natural period 0.4 second, 0.75 second and 1.25 second. Roughly 0.4 second would correspond to the response 4 to 5 storied buildings. 0.75 natural period would correspond to the response of 8 to 9 storied building, and 1.25 corresponds to the response of about 15 storied building, 13 to 15 storied building. So that in a way covers a very broad range of structural systems or the building systems which we can use, and this provides a very, very useful piece of information that can be used in design. And this is a very simple instrument. There is no electrical component or battery component. It's completely passive device, and the response is guaranteed. I mean, we are guaranteed to get the record even whenever the earthquake happens without even any single maintenance visit. And it is these structural response recorders that provided us the valuable information during Bhuj earthquake. We had only one accelegraph record, that too at Ahmedabad, more than 200 kilometers from the epicenter, right? So, but in the epicentral region where near Bhuj, we had structural response recorders scattered all over the Gujarat state, and obviously Gujarat doesn't have very active seismicity. So these stations were not visited for a long time, but only after the 2001 earthquake we visited the place, and we could retrieve about 17 SRR records. And in Anjar, the instrument perished with the building in which it was deployed. So we couldn't get the record from the Anjar station. But I will show you if I can see if I can find something about structural response recorder. Okay, that's interesting. That's a very old World Conference paper by Professor Jay Krishna. So this is the complete design of the recorder. You can see 0.4 second, 0.75 second and 1.25 second, all the diameters and the physical characteristics. This is the drawing of this. So this is the entire pendulum is suspended from this needle, 1-point suspension, and when the base vibrates, so this entire pendulum oscillates. On top of this we have this watch glass, and on top of it rests the needle. So this is what the pendulum looks like eventually, and needle rests at this point and it scratches, and this is held in place by these clips. Okay, so this is a picture of the seismoscope, one particular, and of course this is the original design, where each of these seismoscopes of different natural periods were installed in different boxes, and they were laid out. But subsequent design, we actually reduced the size, and the entire unit was housed in single box, and that was kept in a protective box for in the installation field. So this is one very useful instrument which is guaranteed to work irrespective of whether we have the power, or how old, or where was it required, and whether the station had been visited or not. I mean, it doesn't require any maintenance, and it is sure to give you the response all the time. So okay, so this is another BSSA paper from Professor P.N. Agarwal, again regarding the design of structural response recorders. Here you can see this is the basic suspension system, and this is what I was telling about the 6 pendulum. So 3 pendulum of 1 damping, and this is the needle on which rests on this watch glass, and during the vibration, this earthquake response of this pendulum would be scratched on this watch glass, and at the end we just go there, the team would go there and cover this in a lacquer and dry it out, so that the scratch is preserved, and after this watch glass is brought back on the in the lab, we will process this data. We process this data for further analysis. So this is how it scratches look like, and for different earthquakes at different station, and this instrument has provided lots of useful data, and this gave a major fillip to the strong motion instrumentation program in India. And subsequently we followed it up with our own accelegraph, RESA, Roorkee Earthquake School accelegraph, which was actually the recording of the waveform on the photographic film, analog film. And we went up to 5 versions of RESA. Subsequently we replaced those with digital accelerographs, and we stopped manufacturing our own accelerographs because we couldn't compete in the digital era. So now, of course, nobody works with digital analog instruments, but SRR are still very useful, and they are still deployed in the field, and they do provide useful data whenever earthquake happens. So now we come back to the next instrument. So this is just for information. I don't really believe that any new installations of seismoscopes or structural response recorders are going to be there, because we have stopped manufacturing these SRR. So whatever deployments are there in the field, they are there, but no new installations are taking place unless we decide to revive this program. And and of course nobody is manufacturing it except DEQ IIT Roorkee. So there are no suppliers for SRR as of now in the world. Accelegraph is the most widely used instrument, and they accelegraph output is proportional to the base acceleration. Right. So any sensor, how does it work? Sensors only work with by knowing the response. The basic system theory is you have the input X, it goes through a system, let's say H omega, and it gives us the output YT. So it is this output that we measure. This is the sensor. Output of the sensor is what we measure. Now, knowing the characteristics of the sensor, right? So when I say characteristics, I am referring to here H omega, the frequency response function of the sensor. We try to infer the input XT. So the best example that all of us are familiar with, we use it routinely, is the thermometer. Thermometer, the scale, particularly the mercury based thermometer, the scale is calibrated with respect to the expansion coefficient of mercury, coefficient of thermal expansion of mercury, and the diameter of the capillary. So for each degree of increase in temperature, we know how much volume is going to increase, and knowing the diameter of the capillary, we will know how much progress it was going to make, and that is calibrated, and we directly read the temperature difference in the ambient, whatever is the temperature of the body, by reading it off the scale. So that calibration is based on the sensor characteristics, that is the capillary dimension and the coefficient of thermal expansion of mercury. So that gives us the information, that gives us the relationship between the output and the input, and that's how we figure out what is the input, the temperature rise. In the case of earthquake strong motion records, it is similar thing. It is the output we can measure depending on what kind of sensor it is. We can measure either ground displacement, the ground velocity, or the ground acceleration. Typically, seismometers measure velocity. Displacement is extremely difficult to measure because of the problem of point of reference. We can only measure the relative motion. We cannot measure the absolute motion by remaining in the same frame of reference, and therefore for displacement measurement we really need to go for absolute displacement measurement. We really need to rely on GPS or satellite based measurements. But for velocity, it is based on the simple electromagnetic theory that if a conductor crosses a magnetic field, then it produces the current, right? So that's the Lenz's law. Now the amount of EMF that is generated, that depends on the speed with which it intersects the magnetic field. So the sensor seismometer is essentially a conductor enclosed within a pair of magnets, magnetic field. So it's a magnetic constant magnetic field of known flux, known density is provided. In the middle of that there is a conductor which crosses, which is allowed to move back and forth and according to the motion of the ground, and with the speed at which it intersects the magnetic field, that will produce the EMF. We measure the EMF and that is calibrated against the magnetic field, and we will know what is the velocity, and that's how the seismometers typically work. For accelerometers, we compute the ground compute. Obviously we have a pendulum, similar pendulum kind of a thing. We measure the vibration, but the amplitude of the vibration relative to the base is in certain frequency range. It is proportional to the acceleration of the base, and that is how the earlier analog accelerographs were designed. Very popular accelegraph was Kinematics make SMA1, strong motion accelegraph 1. That was the most popular and most successful instrument, strong motion instrument that was deployed in almost all over the world. And that was based on simple mechanical pendulum spring mass dashpot system of natural frequency reasonably high, of the order of 50 hertz or so, so that and the response we measured, it was optical recording. Obviously, the it exposed on the a photographic film was exposed, the trace of the light source that would move on the that would expose the photographic film, which would be rotating on a drum at a constant speed. So that constant speed was calibrated to the time marks. So that would by knowing the speed of the motor at which the film is being wound, you would know what is the time that is elapsed. So you would get the time marks from that, and it will only the photographic film will only record the trace of the light beam that would be exposed on the film. So there were three components, and there were time marks in between each of those three components: longitudinal, transverse, and vertical sensor of the sensor orientation with respect to the orientation of the box housing. And those were, of course, the sensor orientation were marked during installation, and that gives you the information. So eventually you get a trace. Accelegraph would only produce a trace like this, right? In case of triaxial, there would be, of course, they would all move by the start at the same time. So I can say, so maybe this is longitudinal, this is vertical, and this is transverse. So LVT, that is the sensor orientation. So if this is the let's say if this is the housing of the accelegraph, there would be connectors here, so for the data. So this is longitudinal, this is transverse, and of course there would be vertical. And when we install, we need to keep record of what is the during installation, what is the orientation of this longitudinal sensor and what is the orientation of the transverse sensor, and that orientation has to be a part of sensor orientation, has to be a part of information. Data header. So actual strong motion data, that is the digitized values of this trace, those are the actual strong motion data that we produce. But before that data, there are lots of additional information that needs to be provided, and one of those informations is the sensor orientation. What is the sensor orientation, so that it can be used to resolve in the direction, radial direction and the tangential direction, if we need to make a study of directionality effect and principal component analysis and any such study, right? So determining what is the principal direction and try to find out the azimuthal effects and so on. So without this sensor orientation data information, it is not possible to analyze for those kind of effects. So one thing that is important is what we get from the strong motion accelegraph is kind of this kind of trace. So this is, in case of analog instruments, It is the relative displacement of the pendulum with respect to base is proportional to base acceleration. So essentially it is I just multiply it with a constant of proportionality, and I get this trace amplified by that constant of proportionality is equal to the ground acceleration, and that is what makes life so simple. And this works beautifully. And we have whatever trace we have, we can convert it into the ground acceleration, knowing the scaling factor, which is unique to every sensor. So for whenever we procure these accelerographs, these calibration coefficients are provided, and those are what are used for this calculation conversion. Now all very well, but the problem is okay, does anybody know about the problem that we have here at hand? What is the problem with this kind of traces? Yes, please.
Main position of this.
Yes, we don't know where is the zero line. So we just have this trace on the photographic film without any zero line. And please keep in mind that what I told you earlier, that these instruments are typically kept standalone, and they start recording only after the base acceleration has exceeded certain preset threshold. So that means we do not have initial portion of the record. There was something here which has been lost out. Right, similarly, so this initial portion is lost. So we don't know. If we had this initial portion, probably we would be able to guess when the motion is not so intense, we would be able to guess where is the baseline of the record. But this initial portion is not available. We only have when the motion is strong enough to be recording, to be worthwhile recording it on the photographic film. So this initial portion is lost, and we have to make a guess about the starting conditions. We don't know what is the initial displacement and initial velocity, and of course what is the end value. So there is a lot of approximation, and obviously if I try to fit a baseline if only when I try to fit a baseline I will be able to figure out what is the positive and negative maxima of the motion, what we refer to as peak ground acceleration. Peak ground acceleration value will change if I change the baseline slightly up or down, right? So this baseline correction or reference line adjustment, baseline adjustment, the initial use was baseline correction. Now of course people try to refer to it as adjustment, because correction is too specific and too definitive. We really, adjustment is to convey, indirectly it's more politically correct term, and to convey a sense that we are only doing a guesswork here. We don't really know where the actual zero line is. It's only a guesswork, and most of the time it works, and we are able to get useful information. So this is the most important adjustment that needs to be done on the instrumental data. So first thing is, of course, once we get, in the case of analog accelegraph data, we get it on this photographic film. I will show you the trace that it looks like. So okay, so are you able to see this picture?
No, sir, your screen is not visible.
Oh, okay. No, the
I can't see
video
the picture.
video is not available. Okay, let me try to.
Actually, it is very, but very small. Size is very
Yes, yes,
small.
I got the idea. Let me just try to fix it. Okay. Okay, let me show it from the drive. Okay, so is this visible now? The trace?
Yes, sir, it is
Yeah.
visible.
So this is
Yeah, we can see.
this is the record from strong motion accelegraph SMA1, typical record that was recorded at Uttarkashi during 1991 earthquake. So these are the three traces. This is, as I told you, the orientation of the sensor. So this is N15W, and then this is the fixed trace that is used for uh, alignment, and this is middle trace is the vertical one, again fixed trace, and then N75E, the transverse component, and these are the time marks. This is the duration of which is equivalent to 1 second, and these time marks are based on, calibrated on the basis of the speed of the motor on which is used to wind the film, right? And of course these are the grooves for holding the film on the spindle, and it will keep on moving. So now this is a photographic film. This is a trace on the photographic film, and what is important, what is required is this needs to be converted into digital values first. So what is done is this used to be converted earlier, this used to be converted into digital values by using digitizers. So these values would be picked up by the trace. I mean, whatever is this trace, it would be amplified and optically amplified, and some cursor would be placed, and it would the operator would click it to pick up the data, and that would be calibrated with X coordinate once we design what is the zero line here, and then what is the total time duration, and accordingly it will be position, X position will be marked, and Y position would be based on the operator data. So once we get those digital values, then the process of fitting the baseline to this digitized value of this digitized version of this trace would begin. So that was a very, very involved exercise and very much error prone, but nevertheless it was quite useful, and the operator would pick up the digital values, and obviously it is not possible to provide the uniformly sampled data in that case, so it would be non-uniformly sampled, and that's why it is important to keep track of what is the X value and what is the Y value, and eventually we will get a value of X1, Y1, X2, Y2 up to Xn, Yn. So this pair, data pair, is referred to as uncorrected accelerogram data. Uncorrected accelerogram, and this has to be corrected. I mean, what are the corrections required? Corrections required are: first, instrument correction. And second is of course the baseline. Instrument correction, because this effect, what we are measuring is Yt, right? So in order to infer what is the base motion, what is the input, we need to filter out, we need to eliminate whatever is the sensor characteristic that has gone into this output. So essentially what you typically know as in frequency domain, you call it input output pair, input output relationship. So Y omega is equal to H omega X omega. So essentially I figure out what is X omega by taking the ratio of y omega by h omega, and then again inverting it. So it can be done either in frequency domain, more easily done in frequency domain, or it can also be done in time domain if required. So but easier would be, I mean, this of course, as you can see, the frequency response function is a complex function, and we can have typical frequency response data would be kind of, this is filter response, gain of the filter, and then there would be some phase response as well. So that's the filter response, and we can work out this information by, theoretically it is possible to do so, but practically it is very, very challenging and very, very difficult exercise. So what is done is, allow me to do a little bit of tweaking here. What is done is, if we have omega over omega n, let's say tuning ratio, if I plot it as a ratio of the natural period, excitation frequency versus natural period. So we will find that for a small portion of the beginning tuning ratio, when the excitation frequency of the waveform is very small compared to natural frequency of the oscillator, then this system response filter gain is almost a constant number, right? And when that happens, then the calibration is very simple. It's just a constant proportionality, and I can just multiply this displacement trace with a constant number, and I get the acceleration, and I don't have to worry about instrument correction at all. Instrument correction is just that calibration factor. But if the frequency is somewhere here beyond this range, then the frequency instrument response, applying instrument response becomes very, very complicated. So typically this is what we call as the usable range of frequencies of the accelerometers. So for accelerometers, such that instrument correction involves linear scaling. Outside this range, it is very difficult, and therefore we would only refer to this particular range, and that is roughly about 1/3 or 1/2 of the natural frequency of the oscillator. So typically tuning ratio omega is less than about 1/4 of the natural frequency. Even less than that, I think. So, so how do we do that? So that is the guiding principle of instrument design. How do we design the accelerodgraph? And I need to have the instrument correction that is linear, that can be scaled linearly. So that that requires frequency, frequency range of interest has to be largest frequency, highest frequency that is of interest to me should be at least 1/4 or even smaller the better, of the natural frequency of the system, of the sensor natural frequency. So obviously if my interest is in high frequencies, then I should look at the oscillator, I should look at the sensor whose natural frequency is very high, and that is why typically you would find accelerometer sensors natural frequency of more than 100 hertz. I mean, this is what we call as the lower end strong motion instruments for high frequency vibration, that is typically used for machine vibration and kind of things like that. The natural frequency of accelerometers is even higher. The piezo resistive accelerometers that you see, very small accelerometers. So those accelerometers have a very high natural frequency, and they can record really very high frequencies up to sometimes even up to kilohertz. But for the earthquake engineering perspective, we are not really interested in accelerograms or the frequencies. For earthquake engineering applications, we generally look at frequencies less than 25 hertz. So why 25 hertz? Because 25 hertz corresponds to natural period greater than 1/25, so that is about 0.04 second. So 0.04 second, that's a very short natural period, and that corresponds to structures which are very rigid. So there is no deformation happening there in case of rigid systems. So it actually moves as just as a very stiff block without any deformation, and that is not really matter of concern for design. And so any frequency greater than this is not really worrisome for engineering design as such. So we don't even bother about it. And that is the key for design of the accelerographs, that we are only interested in capturing frequencies below 25 hertz. And of course there is a limitation from the lower end side as well, because when I fit this baseline, it distorts the low frequencies. I can have a parabolic baseline, right? So this kind of parabolic baseline, or even in different segments, different baseline in different segments, it may not have any visible effect or any appreciable effect on the acceleration trace, which is dominated by the high frequencies. But it will have a very significant influence on the displacement trace, and somewhat limited influence on the velocity trace if I try to integrate and derive velocity and displacement from this. And that is why it is little, although we do compute velocity and displacement from strong motion data, the reliability of those displacement and velocity derived from strong motion records is a little suspect. but it's more a case of better than nothing. So, and that actually puts a restriction on the lower end of the frequency. What is the frequency that I need to, I can look at with some degree of confidence. Below that, it is not really possible. And that makes, as I understand, it is the velocity and displacement traces which are of more interest to seismological applications for various reasons. And acceleration, those low velocities would not be appearing in the acceleration trace at all. Those will not be, effect of those will not be visible in the acceleration trace. So trying to draw too much information based on derived velocity and displacement traces from the recorded acceleration trace is really not, has to be taken with a lot of skepticism, I would say, because of the possible distortions in the waveform by this exercise of baseline adjustment. So we will discuss more about it in our next lecture, when I will in next week lecture we will discuss about the modern accelerographs that are used most probably in NHPC deployment. It is those modern accelerographs which we call as force balanced accelerometers, and the accelegraph includes the recording media as well. So those are more reliable than this optical analog accelerographs, but they also come with much higher natural frequency. So for FBA, force balanced accelerometers, so natural frequency is of the order of 100 hertz. For the SMA1, the natural frequency was about 25 hertz and the usable frequency range was only about 10 hertz or so. So next week we will talk briefly about the principle of force balance accelerometers, and then we will move on to the task at hand, that is the baseline adjustment process. So I will stop here. Any questions? Please, welcome. Yep. हाँ कपिल सर.
Actually, this FDE told that they have a natural frequency of 100 hertz, but the usable frequency, like we have discussed, it is about only 0.04 second. That is for the very rigid structure, because 0.04
No,
second is
point.
very rigid.
हाँ.
So then why we are having such this natural frequency up to 100 hertz in FDE?
So it is not the only frequency. It says it is the frequency less than 25 hertz is what is reliable.
Yeah, that's good. That's
So-
okay. But
so-
why we are having this 100 hertz in case of FBA? When we need only up to 25 hertz is okay for us.
हाँ, वो इसलिए है क्योंकि आप ये देखो कि ये जो फ्रीक्वेंसी है ना, ये नेचुरल, दिस इज अवर यूजेबल फ्रीक्वेंसी रेंज एंड दिस इज ओनली अबाउट 1/4 ऑफ द नेचुरल फ्रीक्वेंसी,
Yeah, yeah.
जिसमें कि हमारा इंस्ट्रूमेंट करेक्शन इज ओनली ए लीनियर स्केलिंग, है ना. तो इसमें फिर हमें कोई इंस्ट्रूमेंट करेक्शन करने की जरूरत नहीं होती.
Okay, okay.
अगर हम फ्रीक्वेंसी रेंज बढ़ाएंगे, देन आवर टास्क ऑफ रिट्रीविंग द एक्साइटेशन from the observation of output becomes very, very involved. But if I am operating at this range, which is, you can see, very, very small range actually, then the operation becomes almost automatic. It's only a constant calibration factor, constant proportionality, and the output can be linearly scaled, and we can get the displacement acceleration response.
Yeah, so in that case, if suppose if we have this 100 hertz,
Yeah.
then the whatever data we are having, then we don't need much base correction. You want to say?
बेसलाइन करेक्शन तो जरूरत है, इंस्ट्रूमेंट करेक्शन की जरूरत नहीं है,
Okay. Okay.
है ना. आई टोल्ड यू अबाउट द टू करेक्शंस. Corrections
Yeah, yeah.
required are instrument correction and baseline correction.
Yeah.
So
okay.
this instrument correction we don't need to perform if we are operating in this range, because in that case the instrument correction is only a constant scale, constant scaling. और इसी वजह से because of this reason we try to make natural frequency as large as possible. Of course there is a trade off between the sensitivity. जितनी ज़्यादा हम frequency बढ़ाएंगे natural frequency, वो उतना ही stiff होता जाएगा और उसकी sensitivity उतनी कम होती जाएगी, compromise होती जाएगी. So there is a trade off between the resolution, sensitivity and the natural frequency. But that natural frequency will drive what is the usable range of frequency that we can have. So with a natural frequency of about 100 hertz, we can go up to about 25 hertz resolution. So frequencies up to 25 hertz. So lower frequencies, the restriction comes from the baseline correction. But from the instrument correction side, we can resolve up to I guess 25 hertz. So that usually covers, gives us sufficient range for engineering application.
Now we are having this, some instruments we have this FPA and some are MAMS, this.
Okay.
This, okay.
Yes.
So, and we are using both of them.
Mhm.
So what is your experience about this FPA and MAM system?
I have not really used any MEMS based system. I don't have, we don't have any MEMS based sensors in our lab, but although that is, we are planning to get into the development of MEMS based sensors, because we have now fabrication facility, MEMS based fabrication facility in the institute. So we will probably get into working in this sensor development again. But I guess it is possible, theoretically it is possible to have MEMS based sensor which is also FBA. So theoretically it is possible to derive and develop an FBA sensor using MEMS technology, but physically, see why this FBA is so important for earthquake engineering, or why we are so fixated on FBA, is that its usable frequency range almost starts from 0 hertz. So it has a flat frequency response curve right from DC range. All other all other accelerometer, they would start at a very small frequency, but they will not have any response at the 0 hertz. Right? And why this 0 hertz response is important is in the calibration. I can calibrate this sensor, FBA sensor, which has guaranteed flat response at 0 hertz by using Earth's gravitational field. I don't really need to send the sensor back to manufacturer for calibration, because after some use, all sensors experience some amount of drift in their calibration. But with FBA, I can actually keep on calibrating the sensor in my lab. I just have to tilt it by 90 degree and measure what is the output, and that gives me the calibration with respect to unit G. and I can calibrate my sensor intermittently without any need to send it back to the manufacturer facility. So that is the primary reason why we rely on FBS.
Yeah, and another question is that you told about the direction of the sensor, this direction of the accelegraph.
Yes.
What we are doing in our project, I think in most of the cases we are putting more this according to the north.
Okay, fine. So that's a uniform policy. So then it would be recorded as North N00E and N90E. So
Yeah.
that is fine. But again, that is possible because you have that luxury to orient it any way you want in your dam body. But
Yeah.
typically when these instruments are installed, they are governed by the corner that is available for deployment of this instrument in the building that where you are providing
Yes.
it.
Yes.
So
Yeah,
the
yeah.
building orientation governs the sensor orientation.
And another question is that presently we are putting the sensors in the dam body or dam top in between at some levels in the galleries,
Yes,
and one instrument we are keeping in the free field area.
yes, yes.
So what is your recommendation that what should be the distance of the instrument in case of the free field area? Like generally what we are doing, we are keeping it around say if suppose dam height is 100 meters, so generally we are trying to keep it at least 150 meter or 200 meter like
Mhm.
that from the dam axis.
Yes, typically that is the distance that is taken. Twice the height, 2 times the height of the dam is typically the distance that is taken when the effects of vibration of the dam are taken to subside. Of course, it never subsides. We just assume that influence of dam vibration on the ground vibration at this distance would be small enough to be ignored.
So in that case, we should increase it further, no? You can keep 3 times
Twice,
like that.
anything more than 2 times the dam height.
Okay, okay.
So I mean जितना दूर हो सके उतना अच्छा है, लेकिन obviously you cannot be too greedy. We have to work with whatever we have.
Yeah, yeah, actually somewhere actually we also have very, very big limitations.
Right.
And we cannot increase the distance
Yeah.
like that. Because you have to have all other
Ah.
facilities like
Of
security
course.
plus the land connection, power connections, everything you have to work out.
चाहने के लिए तो पूरा आसमान चाहिए, लेकिन मिलता तो नहीं है.
मिलता तो नहीं है, सही बात जी। कई प्रोजेक्ट्स में हम लोगों को भी प्रॉब्लम आती है ये,
हाँ।
बट हम लोग कोशिश करते हैं कि हो जाए तो अच्छा है।
Right, right. So
आजकल एक्चुअली बहुत अच्छा रहा और काफी हम लोग जो हमारे साथ में लोग जुड़े हैं, आई थिंक ये बहुत हम लोगों के लिए फॉर्चुनेट हैं सभी लोग कि आप लोग